Pressure sensor. A pressure sensor is a device for pressure measurement of a gases or liquids. Pressure is an expression of the force required to stop fluid from expanding, and is usually stated in terms of force per unit area. A pressure sensor usually acts as a transducer. It generates a signal as a function of the pressure imposed. Pressure sensors are used for control and monitoring in thousands of everyday applications. Pressure sensor can also be used to indirectly measure other variables such as fluid or gas flow, speed, water level, and altitude. Pressure sensor can alternatively be called pressure transducer, pressure transmitters, pressure senders, pressure indicators, piezometers, and manometers, among other names. Pressure sensor can vary drastically in technology, design, performance, application, suitability, and cost. A conservative estimate would be that there may be over 50 technologies and at least 300 companies making pressure sensor worldwide.
Hi, I'm John Christopher Onahon and I pick strain gauge pressure sensor. What is strain gauge pressure sensor? A strain gauge pressure sensor, sometimes referred to as a strain gauge, is a sensor whose resistance varies with applied force. It converts force, pressure, tension, weight, and etc. into a change in electrical resistance, which can then be measured. What is the purpose of strain gauge pressure sensor? A strain gauge is an electrical sensor. They are used to measure and monitor strain. They are sometimes used as part of different sensor, load cells, pressure, transducers, and others. What is the working principle of strain gauge pressure sensor? A strain gauge works on the principle of electrical conductance and its dependence on the conductor's geometry. Whenever a conductor is stretched within the limits of its elasticity, it does not break but gets narrower and longer. Application of strain gauge pressure sensor. Used within load cells. Strain gauges are used within load cells. They measure the strain and stress the load cell is under to determine weight and quantities. They can also be incorporated into other sensors, including pressure transducer, to help with pressure measuring. It can be used to test vehicles, ship hulls, dams, and oil drilling platforms. Data sheet. Strain gauge pressure sensor with a millivolt output direct from a 4-arm whetstone bridge strain gauge circuit, and pressure ranges from 10 barge up to 1000 barge. That's all.
Good evening, I'm Marjune Lahinao. My report is for application piezoelectrical pressure sensors. The robustness, high frequency, and rapid response time of piezoelectric pressure sensors means they can be used in a wide range of industrial and aerospace applications where they'll be exposed to high temperature and pressures. They are often used of measuring dynamic pressure, for example, in turbulence, blast, and in engaged conversations. These all require fast response, ruggedness, and wide range of operation. They are sensitivity and low power. Conception also makes them useful for some medical applications. For example, a thin film plastic sensors can be attached to the skin and used for real-time monitoring of the artificial pulse. So, for working principle, when a force is applied to a piezoelectric materials, An electric change is generated across the face of the crystal. This can be measured as a voltage proportional to pressure. This also an inverse piezoelectric effect. When applying a voltage to the material will cause it to change shape. A given static force results in an corresponding change across the sensor. However, this will leak away over time due to inverse insulations. The material sensors resistant to attach electronics and etc. As the result, piezoelectric sensors are not normally suitable for measuring static pressure. The output signal will gradually drop to zero. Even the pressures of constant, they are, however, sensitive to dynamic change in pressure across a wide range of frequencies and pressures. The dynamic sensitivity means are good measuring small change in the pressure open a high pressure environment.
A capacitor consists of two parallel conducting plates separated by a small gap. The capacitance is defined by where epsilon r is the dielectric constant of the material between the plates. This is 1 for a vacuum. Epsilon 0 is the electric constant, equal to 8.854 times by 1012 force over mass. A is the area of the plates. D is the distance between the plates. Changing any of the variables will cause a corresponding change in the capacitance. The easiest one to control is the spacing. This can be done by making one or both of the plates a diaphragm that is deflected by changes in pressure. Typically, one electrode is a pressure-sensitive diaphragm and the other is fixed. An example of a capacitive pressure sensor is shown to the right. An easy way of measuring the change in capacitance is to make it part of a tuned circuit, typically consisting of the capacitive sensor plus an inductor. This can either change the frequency of an oscillator or the AC coupling of a resonant circuit. Application: capacitive pressure sensors are often used to measure gas or liquid pressure in jet engines, car tires, the human body, and many other places, but they can also be used as tactile sensors in wearable devices or to measure the pressure applied to a switch or keyboard. They are particularly versatile in part due to their mechanical simplicity, so can be used in demanding environments. Capacitive sensors can be used for absolute gauge, relative, or differential pressure measurements. And the datasheet will be shown after this video.